So yesterday we talked about exponential growth. So we read a story called One Grain of Rice. Owen, take your headphone out. Apparently it's a big surprise to everybody every day that you're not allowed to wear headphones during the lesson. So I will remind you, don't wear headphones during the lesson. Okay, so we talked about our One Grain of Rice story and how a village girl gets more and more grains of rice every day. Her amount doubles each day, and then eventually at the end of that she has like 536 million grains of rice, and altogether she got 1 billion grains of rice. So the idea is that when we talk about exponential growth, we're talking about something that gets really big really quickly, okay, when something is growing by a variety of exponents. So today we're going to talk about exponential decay. And with exponential decay, oops, wrong one. With exponential decay, it's essentially the reverse of exponential growth. So something will start at a certain value, and if exponential growth gets really big really quickly, exponential decay is getting really small really quickly. So one thing that you will see in today's lesson is half-life. And when we see half-life, that means the amount of time that it takes for something to be cut in half. So there's no such thing as a full life. So if the half-life is 2 years, that doesn't mean it's going to be gone in 2 years. It means every 2 years the amount that we have is cut in half, and then in the next 2 years that amount that we have is cut in half, and cut in half, and cut in half, okay? So half-life, we're talking about cutting something in half or dividing by 2 essentially, or multiplying by 1/2. Okay, so yesterday we graphed for our bacteria cell, very first example, we graphed an example of what an exponential growth equation looks like. And it was something like this. So it started small, and then it got really big really quickly. So it kind of shoots up toward the right. When we talk about exponential decay, it kind of looks like this graph, but flipped horizontally. So what it looks like is starting pretty big, and then that wasn't great, getting really small really quickly. So it will kind of curve down toward the right. Oops. Ugh. Okay. There we go. Oh, and it did it again. There. Okay, so it starts big and it gets really small really quickly. Now, let's think theoretically here. Theoretically, if I have 100 of something and I continually cut it in half and cut it in half and cut it in half and cut it in half, is that thing ever going to be 0? No, because it's going to just get infinitely smaller and smaller and smaller and smaller, right? Even when I get down to like 1, when I cut 1 in half, now I have 0.5. And when I cut 0.5 in half, now I have 0.25. When I cut that in half, and so on and so on and so on. So I'm just going to get smaller and smaller and smaller amounts. Theoretically, when we're talking about like substances, like atoms and things like that, those things eventually get so small that we, as humans, can't detect them, right? Or you would need like very fine instruments to be able to detect the remainder of whatever's left there. So theoretically, this decay graph right here is actually never going to touch 0. It's never going to be 0. It's just going to get tinier and tinier and tinier and tinier. So for that reason, the exponential growth and the exponential decay equations actually have they have asymptotes along the axes, so, or just the, I should say just the x-axis.
Never touches 0 on the x.
Right? Yep. This thing hates me. Let's try this, see if this works. There we go. Okay, so we've got asymptotes right on there. Sorry, I know that's kind of hard for you guys to see. Should have done it in red. There. Okay, now of course if I take these graphs and I start transforming them and shifting them around, they will cross over 0, but for basic functions like exponential growth and decay, theoretically they will never touch 0. They'll just get infinitely close but never cross. All right, so there's our graphs. All right, so we're going to take a look at some examples today that deal with decay. We are still going to use the formula that I introduced to you yesterday, but instead of B being something like 2 or 3, B will be something between 0 and 1 if it's decay. Okay, so let's take a look at a nuclear power plant example. So nuclear power plants use uranium-239 as a power source. Uranium-239 has a half-life, okay, there's that word that we just talked about, I'm going to underline that, of about 2 years. Okay, 2 years in the context of this question is probably an important variable or part of an important variable, so let's underline that as well. Make a chart from the amount of a 1,000 milligram sample that will be left after 10 years. Okay, so 10 years is also something that has to do with time. So usually the things that have to do with time are together here. Okay, so total time here, we're looking at a span of 10 years, but every 2 years, our amount of uranium is actually cut in half. Okay, so we're going to go, because it's being cut in half every 2 years, I'm going to have my, my years go by 2's here, just so we can kind of track that way. So we're going to do at year 0, so the initial value that we have, and then every 2 years from there, 2, 4, 6, 8, and up to 10. And then the number of half-lives that will happen, because half-lives are happening every 2 years. Of course, at the beginning, no half-lives have happened, but after 2 years, how many times have we halved the original sample? Paige? 1. And then after 4 years, we've halved the original sample twice. Yep, and so on. So 3, 4, and 5. Okay, our initial sample was 1,000 milligrams. Okay, and I should be able just to create the rest of these just by halving that sample, or dividing it by 2, in other words. So after 2 years, how much is left? 500 milligrams, good. And then after 4 years, good. After 6 years, 125, good. After 8 years, yep. I do know it. Do you? 62.5, good. And after 10 years? 31.25, very nice. Okay, so to get future values here, we are halving. Lovely, so this is kind of the idea. So we went from something that's at 1,000 milligrams, and then in 10 years, we're now at 31. So the half-life is pretty long for this, actually. 2 years is a long time for something to be halved. But that's why things that, when there's like a nuclear power plant explosion or something like that, that's why it takes quite a while for those areas to return back to normal and things like that. It highly affects the areas around it. And eventually, it's going to take quite a long time before we reach levels of radioactivity that are actually safe for people to be around. That's why they kind of like, if a nuclear power plant ever, you know, if anything ever goes wrong with that and there's any kind of like combustion or whatever, it's really unsafe because those levels of radiation remain for a while. Paige?
What is a half-life?
Half-life is the time it takes for that amount to be cut in half.
Wait, but like, what is, how could it have a half-life of 2 years?
So it takes 2 years for any initial amount of something that we have to, like elements, especially like radioactive elements like this, they do what we call decay. So these radioactive elements, will kind of like break apart and reactions will happen and those radioactive.
2 years for it to be.
Right, right. Does that make sense? Okay, Carla?
So in the case where we went by like at intervals of 2 years, that's because the half-life was 2.
Right.
So we went 0 to because like.
Yep. Okay, so our equation, just to remind you back from yesterday, our equation that we were working with was A times b to the x, where y is the future value and x is total time over the time for a half-life. So here our A value, the initial amount, is 1,000 milligrams. And B, because we're dealing with the amount being halved every time, that is our decay factor. So our decay factor, anytime you see half-life, your B will be half. So our general formula here, if I want to calculate, is going to be 1,000 times a half to the exponent x. Okay, so this question asks us how much remains after 25 years. Yes, of course, I can make my table and I can keep going with this, but I think if we have a general equation, we should be able to calculate this relatively quickly. We have 1,000 and then a half, and then part of x, so the x part of this, x is going to be equal to total time, t, over the time for one half-life to happen. How long does one half-life take? What does our question say? 2 years. 2 years, okay. So this is actually what I'm going to sub in for x in my formula below. Okay? So this is our main equation, but just be aware that x is equal to t over 2. Okay, so in our case, actually, we can just enter in the 25 years here. Guess we'll just plug that in initially. So 2 years, making sure that our units are the same. This is also 25 in years, so that's good. We want 2 years and 25 years. So we're just going to calculate now. So you're going to put into your calculator 1/2 to the exponent 25 over 2. Before you ask me, yes, you can use the decimal value of this, but if this were a repeating decimal, I know 25 divided by 2 isn't, but if your exponent were a repeating decimal, we'd want to enter it into our calculator as a fraction. So you guys can practice that now. So when I enter that into my calculator, I will do like half or 0.5 in brackets to the exponent. I'll hit my exponent button, and then I will make a fraction of 25 over 2, or depending on what your calculator does, you might have to just do 25 divided by 2. And then we will multiply that by 1,000 once we have that answer.
Why isn't it just 500?
Bed mass, so I want to do exponents before I do multiplication of the 1,000 by the half. Okay, so this part we need to do first, and then we can multiply that answer by 1,000. Follow bed mass, people. Okay, let's see what we can get for this. Carla, what'd you get?
0.00172633.
I don't think so. Try again.
Yeah, that's what it is.
I got 6250. Takes that 200.
I don't think it should be less than 1,000, right? Because 1,000 is being halved from the initial value. So let me just check here. 0.5 to the exponent. Oh, this is a bad calculator.
I got 2.44.
That sounds more familiar to me.
Yeah, that and then the number you want.
To the exponent, 25 over 2 times 1,000. I got 0.1726. Don't forget to multiply by 1,000 at the end.
Was I right with the 2.44?
No, it's 0.1726.
So what do you do?
Okay? So, okay, everybody, let's just try this together. You're entering in 1/2 into your calculator. You can put it in brackets or whatever. You can enter it in as 0.5. That's fine, yep. Now you're going to hit your exponent button and open up a bracket and do 25 divided by 2 and close your bracket. Yep. Or if your calculator lets you input fractions, you can do the fraction button as well. That's fine.
I got 1.726 to the power of 10 to the
Okay, so now we have to multiply that answer by 1,000. So just do times 1,000 and you should have our 0.1726. Okay, if you're having trouble, I'll come later and I'll take a look at your calculator and see what you're entering in and help you. Okay, so therefore, after 25 years, (0.127 or 1726 milligrams of uranium, I think it was 239, remains. Yes, 239. Okay. Can I scroll? All right, let's take a look at another element here. Plutonium-239 has a half-life, so there's that half-life thing again. When I see half-life, I know my B is a half. That's talking about my decay factor of 2 years, or 24 years, sorry. Okay, that has to do with time. So that part is going to have to do with X. Find the amount of a 50 milligram sample after 35 years. That also has to do with X. And then the 50 milligram sample, is that our future amount or our initial amount? Okay, so A is 50. And then X. What's the total time span that we're looking at here? 35. So it's not always the bigger number over the smaller number. It's whatever time period you're looking at, right? So my X is going to be the total time over the half-life period. So how long does it take for a half-life to happen? So 35 over 24. Okay, and this is probably a case, I'm guessing. Yeah, we have a repeating decimal here, so we'd like to leave this as a fraction when we enter it into our equation here. And y is our unknown. That's what we're trying to find, future amount. Okay, so let's plug into our formula. Okay, you get a chance to practice again entering into your calculator, see what you can do here. So remember, we're following BEDMAS. You do the exponent on the half first, and then you can multiply that answer by 50. Anyone want to tell us what they got? Ivana? 18.2. Did you get the same thing? Okay. Is it exactly 18.2?
18.95.
Okay. So maybe we can say in our final answer it's about 18.2. 18.2 what? What did we just find?
What?
I'm talking, yeah, milligrams, yeah, units of measurement. Okay, so about 18.2 milligrams. Therefore, so the interpretation of our answer is our therefore sentence. Therefore, after 35 years, there's 18.2 milligrams of plutonium remaining. Okay, so those are half-life examples. Just because we're dealing with decay doesn't mean all of our examples are going to be half-life examples. I could have decay by any factor if b is between 0 and 1, okay? If b is 1, that's neither growth or decay, and if b is 0, you don't have a function, so that doesn't really work. So if I have something greater than 1, I'm talking about growth for b, but if I have something between 0 and 1, I'm talking about decay. So anything between 0 and 1 could be 0.75, could be 0.5, like these questions, any number that you can think of between there. Okay, so yesterday we talked about, and you also had in your homework, growth by a percent. And we also talked about decay by a percent. So when we have decay by a percent, I want to do, so for instance, in this scenario, you're buying a new car and the car decreases in value by 16% every year. We want to know how much value remains in 8 years. So if I decrease by 16% every year, how much value remains every year? Not as a decimal, as a percent for now. Value remaining. If I decrease by 16%, what's left? 84%. So the value remaining is 84%. And that's what I'm interested in. I'm interested in the worth, the value remaining. Okay? So here, when I state my B value, I actually calculate this by doing 100% minus the decay percent. Okay, so in this scenario, we're doing 100 minus 16 to get that 84 remaining. Now, when I state this as my B value, I'm going to state the percent as a decimal. Okay, so it'll be 0.84. Okay, is this a number between 0 and 1? Yes. Okay, so that's decay. My initial value, my A, is 24,000. Okay? Y is my question mark. I don't know how much it's worth after. And then X has two components. What's the total time span that we're looking at here? What is the decay period? 1 year. Every year. This is 1 year. So really, this is 8 over 1, which just gives us an X value of 8. Okay, so we're going to enter this into our equation. 24,000 times 0.84 to the exponent 8. Follow BEDMAS rules, please. Did everybody else get that? 5,000, sorry, tell me the rest, Daniel. Okay. And we are rounding this to 2 decimal places for a specific reason. What is that reason? It's money, yep. So, yep, good. So therefore, after 8 years, the car is worth $5,949.02. Horrible investment cars are. Any questions for this guy? Good?
No.
Okay. Good? Okay. All right, last one. So things like decay rates are very important. So Paige, you were asking me earlier about like what is a half-life, like how do things decay, stuff like that. So let's imagine like this scenario tells us about like taking an Advil. You guys know how like you look on the back of the pill bottle and it says like the recommended dosage and stuff like that. And sometimes certain medications or just like regular kind of over-the-counter, not over-the-counter stuff like Advil, those things still have recommended dosages, and sometimes they will even have, they'll say like, don't take more than this many pills per day, right? So things like decay factors are important here because when I take an Advil, that thing doesn't remain in my system forever, right? Eventually that breaks down and it goes out of my body. But if I take too much and I haven't taken a look at this recommended dose here, I may be filling my system with more than I can actually handle based on how quickly that thing decays in my system, right? So I'll take it, it doesn't remain there forever. Can you imagine if all the pills you ever took remained in your body forever? Probably wouldn't be good. So eventually this is going to decay, enters the bloodstream and it exits your body. So these types of things are really important, right, when we talk about like medical doses and things like that. Okay, so an adult is going to take 400 milligrams of Advil. That is our initial value. That's how much is introduced into the system. Okay, each hour. Okay, so little tricky, but this is part of my X value. That is my growth, that's my decay rate. So each hour, the amount of Advil in the adult system decreases by about 29%. This 29% is going to help me figure out our B value and how much will be left after 4 hours. So this is also having to do with time. So we're going to underline that one with blue because both of these have to do with X, time components here. Okay, 29%. What is my B value? If I'm looking for how much Advil remains, so if 29% exits the system each hour, how much remains each hour? Okay, so what should my B value be if it's 71% remaining? Okay, 0 point, just not percent. We already changed it from a percent into a decimal, so 0.71. Okay, so this is from 100% minus 29% to give me 71% remaining. Okay, that's where we get 0.71. Now my X value is going to be total time. What's the total time period that we're looking at here? 4 hours. And how often does it decrease? Every 1 hour, it decreases by 29%. So my X is technically 4 over 1, which gives me 4 here. And my Y is my question mark. How much is left? Okay, so let's enter this in. This should just be a straightforward calculation here. 400 times 0.71 to the exponent 4. What'd you guys get? About 101.65 milligrams. I'll tell you, but usually like you can round your final answer to like 2 or 3 is pretty good. I would say 2 in general, but I'll try to tell you like in each question. Okay, so therefore, after 4 hours, there is 101.65 milligrams of Advil remaining in the adult system. So the second part of this is just like the last follow-up part. Same kind of scenario, so same percent decrease. But in our follow-up scenario, the blood sample is taken after the person has taken the 400 milligram tablet. The amount of Advil in their system when that blood sample is taken is 25.83 milligrams. Can I scroll from this, guys? We okay? Okay. Okay, so follow-up. 400 milligrams is taken. We take a blood sample and we find the amount remaining is 25.83 milligrams. How many hours after the tablet was ingested is the blood sample taken? Okay, so again, we have this initial amount of 400. One more time. There we go. 400. Our B value from part A is still the same. It's still 0.71. Our future value now is 25.83 milligrams. Our X value, remember our X value has two components to it. It has total time. Do we know the amount of total time that has passed between this initial pill that's being taken and then the blood sample? That's what we're looking for. Do we know how long one decay takes? How long does the 29% thing take?
4 hours.
No, 1 hour, right? Each hour, the amount of Advil decreases by 29%. So this is 1 hour. I'm noting the hour here because when I solve for my t up here, it's actually going to come out in the same unit of measurements. Okay, so I can actually just call this t. That's fine. Okay, so let's enter in what we know. We know y is 25.83. We know A is 400. We know B is 0.71. And X is just equal to t over 1, which is t. Okay, so I'm seeing an unknown in an exponent. What do I want to be thinking about when I see an unknown in an exponent? Log. Okay, anytime my variable is in the exponent, log is what helps me do this. We learned about this yesterday. Okay, if you weren't here yesterday, I suggest that you just watch the video. This example might kind of explain it to you a little bit, but the video is up, so I suggest that you watch that part at the very least. Okay, before I use log, I need the base and that unknown in the exponent there. I need this whole part, the 0.71 to the t, isolated on one side. So I'm going to start just by dividing out the 400. Okay, and these will cancel over here.
What is the A and B stand?
A is initial value and B is the growth or decay factor. Okay. Normally I will just leave, like if I'm dealing with a bunch of fractions and stuff like that, we usually don't write decimals within fractions, but in this case, I'm just going to leave it in this exact format for now, and then once I take the log of both sides and I divide out and I calculate, then we can state our final answer in decimals. If you keep throughout a question rounding and rounding and rounding and rounding, your final answer will be pretty far off. So this is actually a finite decimal anyways, like when I divide this at 0.064575 and it stops, but if it repeated forever, I'd probably want to leave it in fraction form. So we're just going to practice with that for now. Okay, so this is the point where I have my exponent and base isolated on one side. So this is where we use that log function that we talked about yesterday, and we log both sides. So we do log of this whole thing and the log of this. And then yesterday we said that the reason why we do this is so that we can get that exponent that's unknown. And the log function actually allows us to take that exponent and move it down as a multiple in front here. So here's what we've got. Okay, this is called power rule, or we called it parachute rule as well. That's what I usually call it. Okay, Carla?
So when you're finding the x value or the exponent,
Yeah.
you're always going to want to use this way where you're using the log, right? Only when you're finding the x.
Yes, only when there's an unknown in the x, yeah.
Okay. Because like
Yeah.
the other ones, you didn't like divide them out. You didn't use log as
Yeah.
the y.
Only log when your unknown is in the exponent.
Okay.
Okay, so guys, don't go log crazy here. We don't want to start logging everything. We only log if the unknown is up in that exponent, okay? Okay, so right now we have t times the log of 0.71. Remember guys, yesterday we talked about if I have the log of 0.71, those guys are now buddies. I can't move each piece individually. I must move this whole log thing right here, the log of this, all together, okay? So I'm going to divide it out because it's being multiplied by t right now. And I want to get t by itself. Okay, so now that we have t by itself, now I would actually try and calculate these things. Again, if I calculate all along, it's going to cause a lot of decimals to be rounded along the way. So I just try to leave everything as exact as possible till we get to the final part here. And the t is by itself, and then I can just calculate. So we're going to calculate. In your calculator, press log. And if your calculator doesn't open a bracket for you, open your own bracket. And you're going to do 25.83 divided by 400. Close your bracket. You can press equals on your calculator and get the value for that. And then you're just going to press divided by log of 0.71. And that will take your answer and divide it by this log of 0.71.
But does it turn it into a positive number?
Yeah, well, if time is negative, that is probably a problem, right? Yeah. So what do we get? 8. Exactly? What was it? Okay, well, I think we can say 8. Okay, if you were having trouble with this, once I assign the homework, I'll come around and you can show me how you're entering it in and I'll help you. So 8, and this is in hours. Remember, I noted that above because it was the decrease period. It took every hour to decrease by 29%. So what we're going to get out here is 8 hours. So therefore, 8 hours must have passed by the time the blood sample was taken. Beauty. Questions on this guy? Okay, so I have a little bit of textbook homework for us. It's 3 questions, 8, 12, and 13, not even all of 8, on page 167. If you don't have your textbook, I'm going to throw the page up here, and I've also attached it to our lesson in the content area in Edsby. There is also